Hello everyone and good morning and welcome to this next lecture, and let us quickly review what we had done in the previous class. So if you remember, we started from the Kepler's law, and we have started from this first integral of motion, that is L equal to mr squared theta dot. So that is when a particle is moving under a central force field, then you have the first two integral of motion you have. One is the angular momentum, and the second one is the total kinetic energy. So we started for this Kepler's second law, which is like area velocity is constant, that the planet sweeps equal area in equal interval of time, so area is going to be equal. So this was pretty straightforward, that half r squared theta dot from this analogy, that angular momentum is constant, that is d dt of and area velocity is going to be constant. Then we move to the third law, that square of the period of revolution, that is the time period, and is proportional to the cube of the semi-major axis. And again you started with the same first equation, integral of motion, that is the angular momentum m square theta dot, and then we did some calculations, and finally you get this. This is what tau square is 4 pi square, and this is cube of the semi-major axis depending upon the m and k. Then we have seen that this, in case of planet sun motion, where k is my g m1 m2, okay, so this is going to be twice pi a cube under root g m1 m2, where this in place of this mass you had to use the reduced mass of the two body, okay, because this is basically my mu, okay, in this here this is my reduced mass mu. Okay, then we had started to learn that what are the conditions for the closed orbit. So because in central field motion, you're going to have a closed orbit, open orbit, and circular orbit. So particularly we are going to learn about the circular orbit, about the center of the force. So if you remember, this is our center of the force, and the potential we talk about is basically the effective potential, that is my VR, which consists of the real potential which is acting, because this is going to be minus k by r, and the corresponding force is k by r square, okay. So and then this is the centrifugal potential energy, and for the particle which is having angular momentum. So the corresponding effective force, if I from physics, so this is minus dv prime by dr is my force. This is my force. This is so if you differentiate it, you're going to get mr cube. Now we had to find the condition for closed orbit, that you have seen that the closed orbit at two positions, that when this is at this minima at this position, and then the closed orbit can be for this E3, that where this is, there are two turning points, okay, with R1 and R2, maximum R min and R man. Then there within this region the particle can have bound or as well as unbound motion. So for a closed orbit, circular orbit, this position is or minima, either minima or maxima. You are going to have an orbit of single constant radius, which is going to be the distance from the center of the force. Okay, distance from the center of the force. For to this length, that is the apsidal distance of so this is going to be the circular orbit. So we know, you know that for finding a maxima or minima for a potential curve, you need to derive that dv prime by dr has to be equal to 0 first, and then to decide whether there is going to be maxima or minima, then you have to find dv prime upon dr square is either it's greater than 0 or less than 0. So now in our case we need a minima to be stable, so that is going to be less than is going to be greater than 0, and we had discussed that y it is has to be greater than 0, y has to be less than 0. Okay, so first condition that f r naught f prime r naught is dv prime by dr is equal to 0. So so if I put this here in this case, so what I'm going to get is this f prime is going to be 0. Okay, so this is f r at this r equal to r naught. R naught is basically this distance, that is r naught. Okay, so from the center to this. And so the requirement, if you put this requirement, that is if r naught is going to be 0, so this is going to f r naught, this is going to be r naught, so this is going to be 0. This becomes f r equal to minus of L square upon m naught r cube, r naught cube. Okay, so which says the force must be because of this has to be attractive. And the second integral of motion, that is for this circular orbit, that is going to be the energy is going to be constant. In addition, the energy of the particle is going to be constant. So at that position, at this position, the r dot is 0. We know that r dot is 0. So then if r dot is 0, so this is not going to contribute this term. So I just have this and this. So total energy is consisting of at r equal to r naught is v r naught and L square by m r naught square. Okay. Now for any attractive central force, it is possible to have a circular orbit, okay, at some arbitrary radius where let's say it is r naught, and provided the angular momentum is given by equation 3. Okay, this, well, this is the condition, that is this is the condition. From here you can find what is the r naught force, you know, m of the particle, you know, r naught where you want the is going to be circular or not. It depends upon this L. What is the provided L is if L is from this m r naught cube f r naught, then only the particle is going to have this circular orbit, and the energy of that should be given by equation 4. Okay, so now you know that if you have a particle of mass m and that is going under this potential, so at particular value of r within this effective potential, if it is going to have a circular motion, that will depend upon what is the angular momentum of that particle, and that will decide that what is going to be the energy and what is going to be the effective force, depending upon what is the r naught at that position. Okay. Now the character of this circular orbit depends on whether the extremum, that's v prime, is a minimum or a maximum, because you know that I can have whether I have this is not, so I can have this is this position that is going to have this circular motion, as well as going to have this circular motion. Then it will decide that this circular orbit is going to be stable or unstable. Okay, because you know that this is my stable equilibrium and this is unstable equilibrium. Okay, because you know that if you see this condition, if v prime r is minimum, then if slightly raise the energy at the given value of L, okay, so above this circular value result in motion which is no longer circular, will still be bound. That means if I give the particle energy more than E4, slightly more than E4, so say this is E4 some epsilon energy, so this is going to be shifted from here to here, and then this particle energy is going to have, say, at this position, this is my E plus epsilon. So then whether this is going to have this circular orbit or not, so then that it will come down. Okay, so this, you know that this is going to be the stable equilibrium. Okay, so if Vr prime is minimum, then if you raise the slightest energy at a given value of L, particular value of L, above this circular position where this R naught in motion, which is no longer circular. So when you raise the energy, so at this position this is not a circular motion, because this position I have two turning points. Okay, so this is no longer circular, will still be bounded stable equilibrium, because this is now in R2 limit R1 and R2. But if the second case, if V prime is the maxima, if V prime is the maxima, so then if you slightly uh, uh, raise the energy at the given value of L, the above the circular orbit in motion, that is unbound and that is going to be unstable. Okay, so this is because if you raise this energy from this position, if this particle is going to have energy at this position, if you raise this energy by epsilon, so this is going to be unbound. This is outside the potential, that it is like a free particle. So this has to be there, because the circular orbit which we are talking about is has to be stable, and it has to be at the minimum position of the potential. Okay, so to find this, you know that you have to apply this d2 v prime by r is has to be greater than 0 for a stable. For positive second derivative, v prime, that is concave up, and then second is d2 v prime for unstable for positive, that is concave down. So first is for this one, and second is for maxima for this one at r equal to r naught. So let us apply that we want this for stable orbit, that is going to be d2 vr upon dr square at r naught is going to be my stable orbit. So if I have my potential as this and corresponding force is given by this, so what I have to do is I have to double differentiate my potential. First differentiation is this one, because this is my dv prime by dr, and this is my dv by dr, and this is my ddr of L square by twice m r square. So this first derivative is done. Now we have to find the derivative of this v prime, that is d2 vr upon this. So I have to have this is my fr, so this is df by dr with this negative sign, that is because f is minus dv by dr, and then I have this L square upon mr cube with the negative sign, and this is r naught at what I am going to calculating as the position of the circular orbit. Then this is same, and this r cube is going to have minus 3 by r4. So this minus, and differential of this is minus 3 by r4. This minus will become plus, and this is 3 L square upon mr naught 4 is has to be greater than 0, because this we want to be positive. This gradient of this potential want to be gradient. So from equation 3, this we have equation 3 that f r naught is minus L square by mr naught cube. So if I divide it by r naught and then divide it by r naught, so this is going to be f r naught by r naught is minus L square by mr naught 4. Okay, divided. So divided means r naught. So this is, so r naught and r naught cube is going to be r naught 4. Okay. So fr upon r naught is L square upon mr naught 4. So we have L square here and mr naught 4. So at place of this I can write this this fr naught upon r naught from this equation 3. So we have this df by dr at calculated r equal to r naught is going to be less than, because this quantity is my fr by r naught. Okay, with this negative, because considering fr naught to be r naught, considering r naught to be negative. Okay, so this is going to be, this quantity is going to be less than 3 fr naught by r naught. So now if I write this as this quantities as say dfr by, if from here fr naught, if I take fr naught say fr from here, and then this is r naught goes up here, so this is r and this is dr at r equal to r naught. Okay, so this is going to be less than 3. Now what is this thing? This dfr, this is nothing but d of log of fr. Okay, and this is r upon dr, so this is 1 upon log of dr, this is into 1 upon d of log of r at r equal to r naught is less than -3. Okay, so if you see that d log f and d log r is r naught is going to be greater than -3. Okay, where we have considered that this fr naught is if fr naught is going to be is negative, if this is going to be negative, this becomes positive. So that's why this is this becomes less than to the greater than. Okay, so the condition is that from here now I'm going to find it that for some potential inverse scalar potential. So you see that here from here we apply fr naught by r naught to put it here, and then this gives us this is -3, and this considering fr naught by r naught to be negative. We are considering fr naught to r naught to be negative, so this becomes positive, and that's why this you get a greater sign here. Okay, so now for a case like my force is this minus k r to the power n, so the stability equation that is equation number 5, that is dfi dr equal to minus fr naught by r naught. So so that is, if I find dfr by dr, so that means this is dfr by dr is less than -3 fr naught by r naught. So if I calculate this as because fr is minus k by r, so this is going to be minus k, and then this is going to be dr of r to the power n, so this is going to be minus k n r to the power n minus 1. So this side is minus k n r to the power n minus 1, and then you have is less than 3 fr naught by r naught, fr naught by r naught. So 3 fr by r, so this is going to 3 fr is minus k r to the power n, and this is r, so this is going to be minus 3 k r to the power n minus 1. So 3 k r to the power n minus 1 with the negative sign, and because this is with the negative sign, so this becomes positive, this plus 3. Okay, so now this r k will cancel out, and then what you have is r n minus 1 and r n minus 1 will cancel out, and you have I have n here, so n is minus here minus n is less than 3, so n is going to be greater than 3, minus 3. Okay, so for this kind of potential is going to be a stable orbit, then the condition is that n is going to be -3, greater than -3. So now you see that if I put n is equal to 1, so if I put n is equal to 1, so this is going to be minus kr, f is minus kr, this is Hooke's law, and if you put n is equal to -2, so this is f is equal to minus kr minus 2, that is minus k by r square, this is going to be the inverse square law. Okay, so for n equal to greater than -3, and this is going to be closed orbit and stable orbit. So a power law, attractive potential varying more slowly than 1 by r square is thus capable of a stable circular orbit for all values of r naught, because in this case we know that there is going to be one minima 1 by r square, so and you're going to have a circular orbit for that condition. Okay, and and this also, because in Hooke's law you have seen that I don't have this potential, that in case of Hooke's law, that is, if you see, the potential was half kx square plus L square by twice mr square. If you have plotted for if this was not 0, L is equal to 0, you have seen that this is just kx square, and when L was not equal to 0, you have seen that the potential was something. When you plot half kx square, this is going to this, and this was coming out to be like this, and then the total potential is like this. So you are going to have a circular orbit at this position. In the same way, in the case of the square law, so when n is greater than -3, in that case you are going to have the circular stable orbit. Okay, this is the condition. In general, so that you can find the circular orbit condition for a general case, like for not otherwise, this is say f is equal to minus k to the power r n, then also you can prove this. This is another way you can show that what is going to be the condition, stability for the circular orbit, because once you have a force, you can find the potential. Okay, so force potential, that is you're going to have when you have a force, then you have the potential. So this is F is equal to minus du by dr. So then you have to integrate it for r, that is going to have, you have to integrate it for to get this du. Okay, so then when you integrate it this force, so then what I'm going to have, this is minus, so you have k already, and then r to the power minus n dr. So what you're going to have is minus r to the power minus n minus 1, and then you have minus n minus 1. Okay, so this is going to have this becomes minus let me try this. So where this is minus of this, so if we take you find this minus, okay, so this, so r to the power minus n, so if you have rn, n plus 1, okay, so this is going to be n plus 1 and n plus 1. Okay, so it's not minus. So then you have r minus n minus 1, and then you're going to have minus n minus 1. So this is going to have n minus 1 is here, and then you're going to have this r to the power, because this negative sign is here, so r to the power n minus 1, and this negative is there. Okay, so this is the potential corresponding to this force, and then the effective potential will be this potential. So effective potential, you know, that is the potential plus L square upon twice mr square. Here this is mu, because this is from this text is from Marion and Thornton book. So you can go through that also from this book. So if I have this k upon this is my original potential Vr, and this is minus potential L square by twice mu square. So now to find the stability condition, we had to first differentiate this dV by dr at r is equal to rho naught. Earlier we decided that rho naught is nothing but if my potential is this is at this point r dot equal to 0, so this is my corresponding rho naught. Okay, so from the force distance, what is this, r is equal to r naught equal to 0, and then if we double differentiate it, this is going to be greater than 0. So if you calculate this dV by dr, so dV by dr, V is minus k n minus 1, so I have V is minus k n minus 1, and then this is 1 upon Rn minus 1, 1 upon Rn minus 1 plus I have L square by twice mu r square, L square by twice mu r square. So if you differentiate it dV by dr, what you're going to get is basically this is if you differentiate it, going to have the force. So your force is minus k by Rn, and that is if you differentiate it, this is going to be this is dV by dr at r is equal to rho is going to be del b by del r, and at r is equal to rho plus del by del r of this L square upon twice mu r square at r is equal to rho. So this is nothing but the force at r is equal to rho. The force is given to you is k upon Rn. So this is going to be k upon rho n, because you're putting r is equal to rho n, and then r square becomes this is going to be 3 upon r cube. So you are differentiating it, so that in this r square and this is r cube. Okay, so 3 is like 2 upon this is 2, the 2 upon r cube, 2 will cancel out, you have r cube at r equal to r naught, and with the negative sign here also. Okay, so what you get is from this relation what you get is if you divide by rho 3, that is k by rho n minus L square upon mu rho 3 equal to 0. If I divide by rho 3 in the denominator, so this will cancel out. So and then I have k upon, this is rho n minus 3, this is rho n minus 3, and minus L square equal to 0. Okay, L square upon mu and equal to 0. So then from this relation, this you can find that rho n minus 3 is going to be mu k upon L square. And then I'm going to have this double differentiation of this quantity is, if we double differentiate it, this is going to be n, it's going to be rho minus n. So if you have, this is k rho minus n, if I am differentiating it with respect to s, so this is going to be minus n rho to the power minus n plus 1, and then what I'm going to get is this is d dr of L square upon mu rho cube. So this is going to be this is proportional to rho to the power minus 3, because d dr of rho minus 3, so r is rho. So this is going to be minus 3 upon differentiating minus 3 upon minus 3 rho minus 3 minus 4. So this is minus 3 minus 1. So this is minus 1. Minus 3 minus 1 is minus 4. So you have rho 4 here, and then you have minus n minus 1. So you have minus n from here, you can have rho minus n plus 1. So though rho to the power n plus 1 is there, and your n is here with k. So this is all a standard differentiation you can do, and this has to be greater than 0. So if you solve this is nk, and then what I'm going to do is, again you can divide this by rho to the power 4, So this divide by rho to the power 4, this will go on, and then rho to the power 4, this is minus 4. So this is n minus 3. So this is going to be n minus 3. So nk n minus 3, 3L square upon mu is greater than 0. So this conditions give you that minus say nk minus nk upon rho n minus 3 is minus 3L square by mu is greater than 0, and I can put the value of rho n minus 3 from here at this place. So this is going to be minus nk, and rho n minus 3 is mu k by L square. So this is 3L square by mu is greater than 0. So what I'm going to get is k will cancel out. I'm going to have L square upon mu. So this is going to give me, minus n L square upon mu is minus 3L square upon mu is greater than 0. So this L square by mu, L square by is not 0. So what I'm going to get is minus n minus 3 is greater than 0. So this is going to be minus n is greater than 3, or n is less than 3. Okay, so this is what you get, n is less than 3 for the potential or the force is given is minus k to the power Rn, or the force is minus k to the power r minus n. Okay, so is earlier you see that you have r to the power n, and then this is r to the power, this is r to the power minus n. Okay, so and this condition is r to the power f is equal to minus k r to the power minus n minus 3. For earlier that was n is less than minus, n was greater than minus 3 and that is less than 3. So both are same depending upon what kind of potential you are considering. Okay, so now you can do one problem, but I'll continue it into my next lecture because time is almost done. So we will meet again quickly soon, and thank you for this lecture.